Good morning, and thank Professor Fernando Langa and the organization for inviting me to give the talk today. And now I'm going to start with the presentation of the results that we have in collaboration with Professor Langa and co-workers that are based on a novel series of small molecules for solution processed organic photovoltaics. So first of all, a brief introduction about photovoltaic technology. The most important thing to know is that only less than the 10% of the energetic demand are supplied by photovoltaic systems. And with, in this market, more than the 85% are covered by silicon photodiodes. And this is because disadvantages, because silicon photodiodes present higher efficiency, more than 35%, and longer lifetime operations. However, some many drawbacks should be pointed out. For example, the high fabrication cost of these technologies, and the other important thing that these materials cannot be recycled. So this is the reason why many research groups are now working on developing new technologies and new materials, with the aim to reduce the cost, the fabrication cost of these devices. So let's start with a little about organic photovoltaic devices. So this kind of systems present this list of advantages, but these are the main drawbacks of these devices. So we think that this is one of the most promising alternatives to silicon photodiodes, because if we could solve these drawbacks, maybe we can compete, or we could compete with the silicon photodiodes. So this is a general scheme of the mechanism in organic photovoltaic devices. So I don't want to get deeper in detail, but the most important thing are these processes here, which are the main loss mechanism in organic photovoltaics. This is called the Gemini recombination that happens when the electron and the corresponding hole cannot overcome the Coulomb attraction, and they return to the ground state. And the other recombination process, which is considered the most important one in these devices, is the non-Gemini recombination that occurs when the electrons are in the acceptor and the hole from the donor recombine here. So this is an example of the structures that we fabricate in our group. So we use titanium indium oxide pre-patterned over a glass substrate. Then we deposit the period PSS thin layer, and then the active layer, which is the most important layer in these devices, and finally the back electrode that in our case is aluminum. So this is the most common structures that these kind of devices could be fabricated, but in our group we always fabricate this kind of structure, the bulk heterojunction systems, and this is because it's a strategy where the donor and acceptor interface is increased, and for the electron it's easier to reach the interface because the distance becomes shorter. So regarding to the organic materials, the design of these materials is a very important step, and this is, for example, some of the design criteria that should be followed. For example, they should have a broad electron absorption, the energy levels should be placed in a correct position, the mobility should be high enough, they should present high solubility for the solution process fabrication, and finally that could adopt morphologies that we can tune easily. So this is an example, so these are the main families of the small molecules-based donor with their respective record efficiencies. But in this talk, we will focus on the push-pull systems. For example, based on this, we think that this kind of molecules are the most promising ones because they present these advantages. So they have compressed band gap, anti-absorption, and they can absorb at longer wavelengths, and at the end, mostly everything could be tuned easily. But the problem with these systems are that are very difficult to choose the correct donor, the correct acceptor, or even the pi bridge between them. So this is the molecules presented in the last talk. So all these molecules will be blended. These molecules were synthesized by Professor Lang and co-workers. So in these molecules, we use D dot as a core and will work as a donor moiety. So in this work, we aim to compare the difference between the pi bridge, between the donor and the acceptor, and we will try to correlate these differences with the final device performance of the cells. So in the case here, we have a TV, for example, 2 and 3, and in case of L4 and L6, one of the alkyl chains is suppressed. So also we compare the acceptor moieties. So in the first 3 molecules, the TCB group will work as an acceptor group, and in case of L6 and this and 5, the DCB group was substituted by the rhodanine, which is a weaker acceptor. So first of all, the field characterization of these blends. This is the light harvesting efficiency. That is a measure that gives us information about the capability of the film to absorb light. So we can see first this downshift when we use DCB or use rhodanine. So in this case, the L5 and L6 are the rhodanine-based molecules. And this is because the rhodanine is less stronger, so these molecules can absorb less light using the same thickness. And also we can observe a redshift in case of L2 and L3. That this shift is because the presence of more sulfur units. So in this graph here, we can see also this difference or maybe we can correlate difference in morphology after different solvent annealing times. And we can see here that also could be shift, mostly or upshift or downshift. That depends on the reorganization of the molecule after this treatment. And in this case, we can see the dependence on the thickness with the light harvesting efficiency. So here we have, for example, 120 nanometers, and here 26 nanometers, I think. So this is the results for all the completed device. So this is the IV curve of using all the molecules. So in this case, we achieved, in case of L1, an outstanding VOC for an organic photovoltaic device. That is probably due to the great position of the energy levels, showed in this picture here. Also here, we obtain an outstanding fill factor, also for an organic photovoltaic device. And finally, the most interesting thing is the outstanding GSC for the molecule L6. And now let's try to explain how this happened, being these molecules very similar between them. So here, if we remember this light harvesting efficiency graph, we can see that in case of L6, the light harvesting is below the L1, for example. But in this case, when we measure the incident photon to current efficiency, or most common known as IQE, we can see that in L6, they present the highest photon conversion. So this will explain this highest photocurrent for this device in compare with the others. And if we integrate these spectra, we should obtain a value of the GAC that should be corresponding to the GAC obtained from IBQ. So this is the charge extraction and transphotovoltaic measurements, which is an optoelectronic technique that we perform in our group. So in this first graph, this gives us information about the number of charges that the system is capable to store. And the other one gives information about the charge lifetime inside the cell. So first of all, we can distinguish here and a first linear trend, here for example, or here. That means that this cell is governed by geometric capacitance. That means that the charges are mostly stored at the electrodes than in the bulk heterojunction systems. And only depends on the area of the device, the distance between both electrodes, and also the electrical characteristics of the material. But for values close to one-sun condition, we can find this exponential trend. That this is exponential because this is when the LUMO of the acceptor material starts to fill by electrons. So in this case, we can say that using these conditions, our cells are working with chemical capacitance. That means that the charges are stored at the bulk of the material. So when we want to calculate these charge lifetimes, we also have to take into account only these values close to one-sun condition, because if not, these lifetimes would mean that this is the time of discharge of the capacitor. So our real values are close to here in all cases. However, these graphs are fitted to a power law, and all the slopes becomes quite unrealistic. That means that all the slopes far from second order decay means that not only non-Geminus recombination is the main loss of this system. So in this case, we should include in the main loss mechanism recombination, for example, at contacts, recombination by transport, etc. So in order to calculate or measure the mobility of these inside these films, we use this method, the space charge limited current, and to overcome this, we have to fabricate this structure. And when we measure the IV curve, we force the cell to work at higher voltages, in this case from till 6 voltage. So in the range when this is at one-sun conditions and in the dark, so in the range where there is no difference between them, we fitted this graph to this plot. So with these values, we can obtain the whole mobility measurements. So here we can compare all the 6 molecules. So, and if we take as a reference the molecule number 1, we can see that if we increase the pi length of the molecules, the whole mobility increase 1 order of magnitude. And then if we substitute the DCV, we use rhodanine instead of DCV, we can also observe that we increase 2 orders of magnitude on the mobility. And finally, if we study the effect of the alkyl chains, we found that with only 1 alkyl chain, the mobility decreased 1 order of magnitude, and the same happened in case of rhodanine molecules, where here decreased also 1 order of magnitude. So with this study, we think that we can find some strategies to trying to correlate this molecular structure with the final or the main loss mechanism that these devices could present. So finally, these are the main conclusions of this study. So these molecules were synthesized and reaching almost a 5% of efficiency. We could obtain an outstanding VOC and GSE. And the presence of TB and alkyl change improved hole mobility but reduced electron hopping. And the use of rhodanine instead of DCB, even the absorption capability is reduced, the hole mobility is increased, and this is why we could obtain higher efficiencies. And we think that in case of molecule number 6, we achieve this compromise between the hole mobility and electron mobility. And now I want to thank Professor Langa and co-workers, also Professor Emilio Palomares and my group, and of course for your attention.